In the previous video, I proposed a low-cost circuit to keep a solar battery bank charged when there is insufficient sunlight for the solar panel by utilizing the existing MPPT solar charge controller as a battery charger and replacing the solar panel with an alternate DC current source. I also discussed a way of handling the short circuit condition that my charge controller would occasionally impose across the solar panel input jacks of the charge controller. Pictured here are the basic components and layout of the circuit from the van's 12-volt DC socket on the left to the solar input jacks of the charge controller on the right. The previous video described the selection of the PTC, which is a temperature-controlled resistor that acts as a self-resetting fuse, and the DC to DC step-up or boost converter, as well as the cost of all the components. Pictured here is my implementation of the circuit described on the previous slide. To use this circuit, I inserted the round 12-volt DC plug into my van's 12-volt DC outlet and inserted the rectangular weather pack connector into a matching connector that I put across the solar input jacks of the solar charge controller. The key components are the 152 watt DC to DC boost converter, a fused 12-volt DC plug, a PTC self-resetting fuse in a fuse holder, and 16 gauge wires to handle the current without risk of fire. Additional items required were some insulated disconnects to splice the various wires together, some electrical tape, and some 3/8 inch plastic conduit to tidy up and protect the wiring. The weather pack connector is optional, but makes it easy to disconnect and reconnect the output of the boost converter to the solar input jacks of the charge controller and prevents accidentally reversing the polarity of the wires. The red-black Anderson connectors, also pictured, are not required, but I introduced those to make it easier to test and experiment with this circuit. Initial testing showed that I never again had a short circuit condition. But there were two problems that I noticed that made it less than ideal. The current was, on average, noticeably less than what it had been without the PTC. And when it reset, it took a very long time to reset due to excessive heat generated by the PTC. While doing a search at DigiKey, I found another PTC that had nearly identical hold current and trip current as the first PTC, but with much greater capacity to dissipate heat. Pictured here is a comparison of the old PTC on the left with the new PTC on the right. Not only is the new one beefier, but it is also much easier to insert into the fuse holder due to the blade-shaped conductors. I have provided the DigiKey part number for that PTC in the description to this video. Pictured here is the revised circuit with the new PTC installed, which quickly recovered after every reset, and the average current was nearly as good as the circuit without the PTC. But I soon discovered another issue, which was that the boost converter could be subject to a flow of current coming from the battery. When the converter output voltage drops below 12.8 volts, which it would do when the PTC resistance increased sufficiently, thus lowering the voltage going to the charge controller. The solar panels don't have that problem because they have blocking diodes. I initially thought of adding this blocking diode to the circuit, but when I realized that the solar panel DC current is floating and not bonded in any way to either the solar battery bank or the van starting battery, but the boost converter is actually bonded to the van starting battery at the negative terminal through the van's 12-volt DC outlet, I decided I needed to do more research on DC to DC boost converters before going any further. I found a good reference on DC to DC boost converters in this paper presented by DigiKey that shows that typical boost converters are subject to short circuits because of their design. It goes on to describe several different strategies for handling a short circuit condition. One way is by specially modifying a boost converter, which would eliminate the need for a PTC. I have provided a link to this paper in the description to this video. I found this additional paper, also presented by DigiKey, that describes the difference between isolated and non-isolated DC to DC boost converters. That made it clear to me that the boost converter I was currently using was non-isolated, and that what I should seek is an isolated boost converter in order to adequately duplicate the floating circuit that exists when using the solar panel. I have also provided a link to the second paper in the description to this video. After searching for an isolated DC to DC boost converter with short circuit protection and at a reasonable cost, I found the following from Victron, the model TR-12/24-5A, which converts 8 to 17 volt DC to 20 to 30 volt DC, user adjustable, with a maximum output power of 120 watts. I am currently evaluating a revised circuit that utilizes the Victron DC to DC boost converter along with a blocking diode and without the PTC, and will present a follow-up video once that testing is complete. Thanks for watching, and stay tuned for part 3.